Welcome to the Missouri Wind and Solar Podcast. I'm your host, Wes Shank, coming to you from our store in Seymour, Missouri. Each week with my co-host and Missouri Wind and Solar's General Manager, David McDaris, we discuss the latest on self-reliant energy. Check out our additional educational information, including dates for our hands-on workshops conducted in Seymour, on our website, windandsolar.com. Thank you for listening to our podcast, and if you haven't already done so, please consider subscribing. I managed to wrangle Sam and David in here today. Well, David's always in here, so I think I've got some contractual obligation.
What else does he do?
It's a good question. If you look at his desk, apparently it's to eat the snacks coming in from the vendors over Christmas. So we've got Sam in here with us today, and what we wanted to talk about. So we touched on this a little bit a couple of weeks ago in our podcast, and that's ferrites. And as we looked at that, I continued to look at that, and I installed a bunch of these out on my place. I kind of thought it'd be a great podcast to kind of delve into that a little bit farther. And let's talk about what they actually do and why I put them out there, and kind of go through that with Sam. And I guess, Sam, the first thing I'd start with is, if you haven't seen them, I guess the thing I would describe them as, it looks kind of like an old school pencil sharpener. I mean, it's about that size. There's a hole running through the middle of it. Now that's one's called a ring ferrite. And what's the other one called?
So you've got a toride, which is the ones that are just a ring.
Right.
And then you've got what's called a clamp-on core, which is the ones that we've been using on solar panels and everything else.
Okay. And that one looks like a big old pencil sharpener. And if you open that up, it looks like, is it just a carbon? What is that core made of?
Okay, so that leads into some of the bullet points that I kind of put down here on my notes. So a ferrite in general is a iron-based core. There will be other materials, manganese, aluminum powder, all sorts of different stuff mixed into the ferrite. In principle, it's a magnetic material that will suppress certain frequencies.
Okay, and that's
what
what I was going to
affects what it suppresses.
And that's what I was going to say. It looks like a cross section of a U magnet, sort of. I mean, it really,
like the old magnetite magnets on the back of TVs and speakers and stuff. Yeah.
Okay, so is there a significance to the size of it? Is bigger is better? The composition, are all ferrites created equal?
No. So the size is not really the important factor as much as it is just about being able to fit your wire through there that you need. The big principle that you're after is the certain material, right? So specifically here, we're interested in type 61 ferrites, which are designed to suppress between 200 megahertz and 1 gigahertz. So very broad band of the higher frequency radio waves, which are what you're going to see from things like lightning EMP and CME.
Right. And then I know when we first started looking at carrying these, you were real specific when we were speccing these out and where we were getting them from.
Yes, because if we had the wrong type, say a type 32, we wouldn't have the same frequency range. It would still perform some of its functions, but it wouldn't be quite right. What we're really looking for is the HF and actually truly the UHF, VHF, and microwave range of electromagnetic fields that we're trying to suppress.
Okay, so what's happening?
Basically what happens is that a ferrite is a type of inductor, right? So if you think about an inductive load, you've heard the term an electric motor or something like that, right? It's got an inrush of current and it takes it a second. David, you've worked around stuff a lot in your life, power tools, that sort of thing. At some point, I'm sure somebody's told you, hey, uncoil that extension cord before you go run that saw or you do this because it won't run right. And some people will go, well, that doesn't make any sense. Why would that happen? Well, what you're doing when you coil an electrical cord like that is that you've created an inductor. And an inductor, because of the way that alternating current flows through the wire, as it passes through its own electromagnetic field from that next coil over, it resists the flow of that AC electricity. And so you're basically creating a bottleneck. Think about a garden hose, and if you kink it up really tight and you coil it up, and then you turn the garden hose on, well, all that water has to go through that garden hose and through those kinks, and it slows it down versus if you just stretched it out straight.
Okay.
Same thing's happening with the electricity. In this case, with a ferrite, we don't have a big coil of wire. We're simply clamping around it, and that helps us a lot because we're able to suppress a specific band or frequency range of electricity. Again, in this case, we're suppressing that VHF, UHF, and the microwave range of radio waves. And in doing that, we're able to select what it is that we're suppressing.
And I think one of the interesting things, the first takeaway is, I'm always the great one of very limited knowledge, it's always great to have me here from that standpoint, is what's interesting there is realizing that while your wiring is insulated, there's still activity that's happening outside of that.
Yes.
That wire. I mean,
so
it's still
technically, AC electrons technically flow along the outside of the wire, not the inside of it. And that's one of the reasons you can use like a stud finder and you'll be able to see, oh, hey, there's a wire here in the wall, is because it has that ability built in to detect those frequencies as they pass along the outside of that cable. Same reason that a lot of your current meters that have a clamp on them, the AC ones, are very, very common because it's easy to detect that EMF as it passes through, and you can use that to determine how many amps are flowing.
But you're not going to get electrocuted because
you're not actually completing the circuit. Yeah.
Interesting. Okay. So we've gone out there, and you know this, you were out there with me when I was doing it. So we've gone out there at various points in the installation, and we've clamped these on. Mm-hmm. Give me some reasons why we clamped them on where we did. There were some specific points along that we installed those.
Right. So we wanted them in this particular instance, for the most part, it's for protecting the panels and the diode box inside. So the further basically wherever the inductor is, in this case, the ferrite clamp on, that's where the electrical suppression starts. And anything after it in the direction of current flow is an antenna again. And so in this case, we're trying to suppress near-miss lightning, that sort of a thing. The closer we have the ferrite core to the diode box, the less antenna there is between the diode box and the ferrite.
So let's break that down a little bit. Because so when we were out there, on the back of each panel, we had our positive and negative coming off the back of the box on the solar panel, and we were pretty much clamping on right there.
As close as we could get.
Right. And so we were taking both the positive and negative, and then we were putting this little barrel, and again, it's about, 2-3 inches tops, something like this, like probably about 2 inches. And we were clamping that on to both of those leads. And so what you're telling me is, so if something happened and that panel had some type of charge that it picked up, however, as it started to try to go to ground, it would come in and... Have I said that wrong?
Kind of, but you're on the right track. Basically, if it tries to complete a circuit through the diode itself, right, into the panel, because you've got a circuit at both ends. You've got the solar panel with the silicone cells and everything all wired together, and then you've also got your charge controller at the other side. Well, if you have an induced field from, say, lightning, right, you've got 150 or 200 feet of wire buried under the ground.
Right.
You've got a really nice antenna buried there in the ground. You've got a really nice ground plane. Well, in having that as close as possible, as the electricity gets a run at it, it can only run on the backside. It can only run 3 inches. There's not enough of an antenna there to matter, right? You can't get enough of an induced field there, and that's why we don't have it out there in the middle someplace.
Okay,
now you've got 20 feet of it.
So slow it down again. So the lightning hits the solar panel or something, right? Because
hits nearby.
If lightning hit it, it'd be a little smoking ruin.
Yeah.
So the power's coming down those two wires. It hits the ferrite. What's it basically doing?
So essentially what happens is that the more current you have and the higher the frequency you have attempting to pass through any inductor, in this case a ferrite, what happens is it basically gets slowed down
and that's probably the key. We're not stopping it, we're slowing it down,
yes,
right?
As we slow it down, because we've created a resistive load now out of that inductor, because an inductor resists the flow of alternating current, if it can't escape anywhere, it turns into heat. Right. So if it can't go through the ferrite, or if it slows it down because you get more and more of a bottleneck, the more current you try to pass through it, the more it bottlenecks. As that happens, the ferrite will get hot momentarily.
I was going to say,
it's going to dissipate that heat back out into the air. And that's what the ferrite does, is it will get warm and it will dissipate. It's the same reason you see heat in things like transformers, which are also an inductive load, is because as the work is being done to them, that energy is transferred. Some of it is lost, parentheses, right? We can't lose energy. It just gets changed from one form to another. But that's why a transformer gets hot. If you look at one through like a thermal imaging device or something, you see that they're screaming hot all the time. And the hotter they get, it's because more loads are passed through them. And so the ferrite will get warm momentarily, and then it will dissipate that heat back out.
Great. So that brings me to a question here that I think some of the followers here would have. So lightning hits the ground, boom, it goes and hits the ferrites. If it does that on our VRD board that's got our surge suppression, it busts the little modules inside the surge suppression. You got to change it. do you have to change the ferrites?
You do not, unless the ferrite is physically damaged. But if the ferrite's physically damaged,
It's blown off the wire.
it would mean that you had basically a direct hit, and the solar panel and everything would be shot at that point. Not only that, but ferrites are used, especially in this situation, in conjunction with lightning arresters like you described, which are varisistors.
And that's those blue, the blue light.
Yes. So whenever we slow down the current, okay, so we've created an area where the current doesn't want to go anymore. Electrons want to take the path of least resistance. Not only now have we slowed it down and are starting to dissipate some of that energy as heat, we now have that surge protection device there ready to go, ready to shunt all of this current to ground. Whenever you combine those two things together, you slow down whatever that pulse is and you redirect it someplace else. It's not perfect, but that's the principle, and it works very well.
Okay, so this surge of power is coming through, hits the ferrite, warms it up, and
to some extent, yeah.
And it may continue on down that wire. But is the fact that we've slowed it down, is that what's going to save things on the other side?
We've slowed it down and we've helped to reduce the voltage, right?
Okay.
So the big thing about diodes, which in your solar panel is what we're concerned about, is that they have a breakdown voltage. So most diodes in solar panels these days are rated between 600 and 1,000 volts. Between the varisistor and the ferrite clamp, you can shunt that down to 400 or 500 volts, which means the diodes will block the reverse current flow and you won't burn the diode or the solar panel. So it's a combination of things. The big one is that we're slowing it down, reducing the voltage, and then we're sending it someplace else. The ferrite core by itself may or may not save it, but when you combine the ferrite, reducing the voltage, and you slow down the current,
we're going for our best shot.
Yeah, we're going for our best shot. But by doing that, you're giving the lightning arrestor more time to act, right? So we've slowed it down, we've reduced the voltage, and now we can pass that current someplace
Okay,
else.
and so taking that in consideration, why does the ferrite not screw with it on a regular basis?
Because induced fields like this are alternating current. We're passing direct current through it from the solar panel. Direct current is not really affected by inductors in any way.
Interesting.
So an inductor resists the flow of alternating current because of the magnetic field it creates.
So
DC doesn't do that.
So you wouldn't put a ferrite on on an AC plug, for instance.
Not around all of the wires. You can put ferrites of specific types and specific frequency ranges on a single phase of an alternating current load. And the problem is that you get what's called ferrite saturation. So you have to be very specific about the type of ferrite that you use. And the ability of those to function is so limited. I mean, you're not suppressing these higher frequencies at that point. So it doesn't really do a lot for you. That's why you see more surge protectors on the AC side, is that if we put a ferrite core around multiple wires, we actually create an inductor and we make it hard to use the AC. If we put one on a single phase, it suppresses such a limited amount that it's not really useful.
Because I know we are prone for rabbit holes, so prepare for one. I know on just any given appliance that you buy, I mean, it's like on the most random things, you'll see that big glob hanging off of it.
It's always DC.
And that's what I was wondering. So it's going to be on the other side of the of our,
like a laptop charger.
Yeah.
Right? If you look at a laptop charger, that is always on the other side, and it's within 4 to 6 inches of the plug that goes in your laptop. It's always right there. And that's because we're reducing the length going into it, and we want it on the DC side.
Okay, that's interesting. But nonetheless, just, if you've wondered what that is and why that's on there, it's a ferrite.
Yeah, it suppresses electromagnetic.
And interesting, I was curious. I mean, and you, if you don't know this, I'm hitting you with questions that I didn't give you a list of.
I didn't get to study for this.
Yeah, you've seen that where those are. It looks like those are looped.
Yes.
Is there some significance to?
Yes, by looping the wire through it, you double the amount of time that the electrons spend passing through there.
Okay.
You increase it. Basically, every time you make a loop, you're essentially doubling the amount of inductance.
So if you got enough room, basically in your hole down through the middle, we could have looped the ones we did. I don't think we have room.
We didn't really have enough room for that. Okay. You might have gotten it in there, but it'd been really tight and hard to close, and then you'd have had pressure pushing out against it. We don't want that, because if it falls off, it does you no good. It's easier to just snap another one on there.
Okay. And so I'm going back in my mind. I know we put those coming out of the solar panels, and trying to think, we put those, it seems like we put those just before we went
into the ground, which is only going to help us, right? So again, we're trying to suppress as much as we can. What would be optimal would be to put all of the stuff in an entire ferrite, conduit, but that's not practical, right? But what we can do, if we've got a long flat run, again, we have a great big antenna buried in the ground. Well, if we put one right there, we've slowed it down once. We put another one on each panel. We've slowed it down again. Not only that, but the path those electrons would have to take, we've slowed it down, and now it's heading towards our varisistor or surge protector inside your combiner box, right? And so now we've already slowed it down once, and if it passes through that box, we've got another additional protection. Technically, you wouldn't have to have one there, but an ounce of prevention is worth a pound of cure.
Yeah, I mean, that ferrite's a heck of a lot cheaper than that FM100 is.
We're talking a $12 Ferrite core versus an $1,100 controller.
That was easy. But we didn't do anything actually in the mechanical room, if I recall.
Right, and we could install additional ones there if need be. It's not going to hurt anything to do that.
But is it going to help?
It could. It could help. You've still got to path the ground through the rest of the equipment and that sort of a thing. You could install additional surge protection there as well.
And now you keep mentioning that, path to ground. Tell me how that's...
So your surge protection device is basically a really rapid switch with an extremely low resistance value. So electrons want to go to the lowest resistance. If you provide them a path to ground that's low resistance, they'll generally take it. And so instead of allowing you to complete the circuit into your solar panel, you would complete the circuit, send the electrons to the dirt, right? Imagine like a fluid system, water, hydraulic oil, whatever. Basically what you're doing is you're generating a great big leak right before something that you don't want to tear up, right? And so you're draining all of that off. It's like a pressure regulator.
Right, but you mentioned that in the context of the ferrite. What is that... am I missing something here in the context of the ferrite?
If you didn't have any sort of grounding, the ferrite isn't going to save you because it's still allowing that high amperage, high voltage into the unit. What we're doing is slowing it down, dissipating some of it, and giving our surge protector more time to react.
Okay, so time to click it over and send it to ground.
Yes.
Okay, that makes sense now. I see what you're saying there. Because if all of a sudden, if it just boom, hit and popped,
right,
then you're strictly relying on your surge suppression to try to
do that, and
to move it to ground fast enough.
Yes, and the speed of the pulse and the voltage of the pulse. And so what we're doing, we're helping to reduce the voltage. We're giving the varisistor more time to react, and reducing the amount of work it has to do.
Okay, excellent. What else do we need to know about the ferrites?
We've covered materials, we've covered coiled extension cords and that sort of thing. Those were the big points that I wanted to touch on about what it was, how it worked, and why it worked, which you asked a good question. Why doesn't it affect the panels normally? That's really the big one. It does help. You were asking about the mechanical room. The big reason you might put some in the mechanical room would be if you went in there and you noticed it was what a radio operator would call electrically noisy. It really shouldn't be. Everything complies with the FCC rules. If you do notice it to be electrically noisy, you could install ferrites to suppress that.
Okay. All right, and just to kind of wrap things up, I mean, we sell them here. We have specifically spec'd out what we want to sell here. Is there a reason that you're aware of to have any kind of different ones than what we carry here? Would there be because there's a ton of them out there. I know there
are lots of reasons for them. Primarily, it would be if you're a radio operator and you're trying to tune equipment to a certain frequency and you want to suppress all other sounds, right? That's really what ferrites are traditionally thought of as being for making what's called an RF choke. So you can suppress certain frequencies, which allows you to hear others better. If I had a radio of some kind that I wanted to suppress, in this case 200 meg and above, right? If I want to suppress the 1 1/4 meter band because I'm trying to listen to something just below that, say it suppresses 200 meg, but I really want to listen to something like 180 meg, which is an oddball frequency. But if we're pretending here. The way the radio wave works, it's not perfectly clean. Radio equipment doesn't do that. You get some stuff on the edges that's not right. It's outside the frequency.
Right,
it's the reason that if you have a radio, you tune in, you hear static, and there it is. Right, and then you tune out, and there it's gone. Because the radio wave, it's just like a sound wave, right? It's making an up and down wave. And at the peaks of that and the valleys of that, you get some feathering at those edges. And
so you're just getting rid of that.
Yes, you can clean that up.
But for anything we're doing with wind and solar or any of that, I mean, this is really the optimum.
Really, this is the optimal. I mean, you could use a Type 32, but it's not as broadbanding. They're going to cost the same. There's no real reason to use anything other than a Type 61 in our application.
Okay. The last question I've got, in whatever you got over there, we talked about the clamp on. where would we have used the ring?
The torides?
Yeah.
So the torides are nice because they can be cheaper.
And real quick, I know we're using technical. So the clamp-on we described, what Sam's saying is toride. I mean, it basically looks like a big wedding ring.
Yeah.
I mean, it's about that size. I mean, so.
Yeah, some of them are even bigger than that. But yeah, the reason you would use a toride would be like on your charge controllers, right? We don't have MC4 connectors. We don't have any big terminals on the end. I can fit wires through it easily. With a solar panel wire like that, if I'd have wanted to install a ring ferrite out there, a toride, I would have to have a ring that was big enough that I could pass my MC4 connectors through, my wire through.
Gotcha.
The clamp-on cores, I think the hole diameter is not even quite 3/4 of an inch.
Yeah.
But then on the rings, because of how big your connectors are, even if you stacked them just right, you'd still have to have a ring that was over 1.25 inches in diameter. It's a lot bigger than it needs to be, then it costs more. By comparison, coming out of the combiner box, we didn't have any MC4s, and we were putting the MC4s on. Technically, we could have put a ring there, and it would have maybe saved a couple bucks. But again, we're talking a $7 ring or a $12 or $15 clamp-on. We know that we need the MC4s, and we were like, okay, where can we install additional? So we just put a clamp on.
So are those? And again, like I said, the size of those is like a big wedding band sort of thing.
Charge
I mean,
power inverters would be the place for those.
Does one work, or do you need 5, or does 12 better than 2?
Have as many as you want. There's a diminishing return after about 5 ferrites. Typically, you start to notice a reduction in effectiveness. Generally speaking, though, in a situation like that, you would just have 1 or 2, depending on the gauge of wire you're using.
Okay.
A lot of times, those rings, again, like a big wedding band, that's perfect for number 4 and number 2 cable coming out of a charge controller. Most power inverters are going to be in that number 2 to the 4-aught range, which you can still fit through.
Because compared to that clamp-on, those clamp-ons are huge.
Yes.
Compared to the toride.
So what about the jacketing on the actual wire? Does this just go over the jacket, or do you have to
it goes over the jacket. No, if you strip it out, you've now created a conductive point, and you're going to have big gobs of sparks, and it's not going to be a good day.
Okay.
No, so again, we're suppressing.
So you never put it over the bare copper.
No, you don't want to put it over bare copper. And again, specifically, we're stopping radio waves, which are passing along the outside of the wire, right?
Okay.
You don't often think of radio waves as electricity, but that's what they are, right? They're electromagnetic radiation.
Right.
And so we're suppressing that, which is not actually moving through the wire. It's moving along the outside of it. Since we're just trying to suppress something on the outside of it, all we have to do is be right there.
Okay. And the other thing you said earlier, and so I just want to get this clarification for everybody that's listening. You said while making a loop, you double the length of...
Right, because you put the inductor in there twice.
You put it in there twice. So would you recommend making a loop?
If you have the room. If you have the room, yes.
Right. So even coming out of a solar panel, make a loop and then go on down.
If you can. Okay. And it's not always possible, right? Especially if
on ours, the wire would have been too...
Right. In the jacket.
I get it. But if it's possible, you have the room and you have the correct size of ferrite to go around it, you can...
Yes.
Okay. All right.
Yep.
All right. Did we miss anything, Sam?
No, I think we've covered everything, Wes.
Okay. And again, this is something we carry here in the store. We can ship them out. It's a great, this thing is like having a fuse. I mean, it's one of the best insurance devices, super inexpensive, and they're absolutely, it takes 5 seconds to put it on. And there's just absolutely no reason why you shouldn't at least have these on your solar panels. Okay. Sam, thanks for coming in today.
Anytime, Wes.
All right. Thanks, Sam.
I'll see you later, I'm sure. All right. Thanks a lot for tuning in. Thank you for downloading and listening to the podcast today. If you have a question you'd like to hear us discuss on the podcast, or just want to say hello, email us at radio@windandsolar.com. As always, check out our store at windandsolar.com and buy some stuff. Your financial support underwrites our educational outreach, like the podcast, YouTube channel, and local STEM collaboration. It also keeps Lucy and her doggy chicken treats. Thanks again for listening.